So let's have now a very high overview of what a neural network is. So neural networks started as a way to mimic or to try to simulate how neurons behaved. So that is why the name neural networks. So the neuron is a cell that that composes our nervous system, and there are millions and millions and millions of these kind of cells, and these kind of cells, they have, all of them have the same structure. So they have a cell body, and the cell body receives inputs from the nearby neurons through the dendrites. So the dendrites is the input to the cell, and then all this information is combined into a new signal that is transmitted through to the next to the next neurons through the axon. So the axon combines all this information given by the dendrites in a non-linear way, and it is transmitted to the next neurons. All the encoding has to do with the frequency of spiking, and we will not enter into the physiology of this. So a way to mimic that was this one. So you have a number of inputs that through the dendrites. Sometimes you have thousands of inputs and also thousands of outputs. All the outputs are supposed to be the same, and all the inputs are coming from the previous neurons. So you are receiving information from thousands of previous neurons, and you combine it. And the way to combine this is through some weights, and there is a bias. So there is a kind of even if all the inputs are off, so there is no input, still you are firing at a given rate. So this is the bias. And then you go through a nonlinear function, that is the action of the axon, and then you transmit this signal to the next neurons. And here you have a more detailed model of that. So you have all the inputs from the previous neurons are weighted by different weights, and there is an extra entry, that is the one from the bias. So this is this B that is coming here, so it is always coming with also as an input, and you may think of this as 1. And then it goes through a nonlinear function f, whatever it is, we will see it later, and you produce an output. So it is a way just to mimic how neurons work. But it turned out that when you concatenate many of these neurons, all this concatenation is called a neural network. And these neural networks were extremely good models for modeling data. So if you have a set of observations, x1 and x2, and each point here is one of those observations, then with a neural network, given x1, I can tell you what x2 will be. So if you have xy or x1, x2 components, observations, then the neural network can reproduce these observations up to an arbitrary level of accuracy. And the more neurons you have, the more freedom you have to adapt to the observed data. So when you concatenate many neurons of this kind, then we see that each one of these units is just the neural network we saw before. But then what we see is that we have a set of inputs. This set of inputs are distributed to all the neurons in one of the layers, and you have the different weights of that layer. And then these 4 neurons, produce an output that go through again some weights to a couple of neurons, and then this information is forwarded for many layers. So the parameters of this function are the different weights. So these weights you have to learn. That is what we do through deep learning. So the learning refers to the fact that you have to learn, you have to figure out what the weights are. And then for figuring that out, you can compare, this is the input, this is the output. So you have some observed outputs, and then you can you can compare your observed outputs to your predicted outputs, and that comparison will tell you if those are very similar or not. So here we would have the space of weights. Because of the dimensionality constraints, we can only show here a couple of weights. So, and for every combination of weights, you will have a similarity. So this similarity is somehow represented here. So the higher the value, the less similar they are, and the lower the value, the most similar they are. Don't pay attention to the sign. I just took a couple of figures that illustrate this idea as well. So the problem with this function, with this similarity function, is that because we have so many weights, it is very difficult to find what is the global minimum. This is what is represented here. There are a number of local minima, there is also one global minimum, and you want to find this global minimum, but finding the global minimum is very difficult. It depends on your optimization algorithm. We will talk a lot about these optimization algorithms later, and some of them, and one of the most successful ones at the moment, are these somehow stochastic gradient descent. So somehow gradient descent, a standard gradient descent, would go smoothly to the global minimum when it exists, and these versions, stochastic versions, what they do is they wander around. Sometimes they go in the wrong direction, but very often, as long as on average you are moving towards the minimum, eventually you will find the minimum. So this has been one of the big advances that made neural networks possible today. So why deep learning now? So because we have so many parameters, we will see that in neural networks we can have, depending on how many layers you can have a few million parameters. So here we just had a couple of them. But when you have millions, then for having millions, you need a lot of data to train. So you need a lot of input-output pairs so that you can learn what are the weights that make this input and output match. And so you need a lot of training examples. That means big data, and only now in the last decade or 15-20 years, if you want, we have access to so much data so that we can learn many millions of parameters. Secondly, all this forward propagation and the backward propagation, especially the backward propagation, it is quite computationally expensive. But the GPUs have largely accelerated the calculation, and currently the two main libraries used for this are these TensorFlow and Keras coming from Google, and PyTorch coming from Facebook. There has been also a lot of advances in stochastic optimization. So these algorithms here that we mentioned, that they try to escape from local minima. And there has been a lot of advances in network architectures. So what we refer by network architectures is somehow represented here in these ideas. So there are many different ways of connecting the neurons, and also there are different kind of neurons. We have just seen one of them, but you see here different kind of neurons that we can have. We will see many of them along the course. At the moment, don't pay attention. You can also connect them in very different ways. Even the output of one can be the input of itself. So why not connecting a neuron to itself? It is also possible. It is not only necessary to go in a forward direction. So you can make backward loops, and also you can combine them in very different ways. So this has been one of the big changes. Here is another very popular neural network architecture, that is a U-Net. So in U-Net you have an input here, and then you have some convolutional layers. We don't know yet what they are, but some way to define these weights that we had before. So you define your weights, you propagate forward, and then you reduce the size of those images. We will see all these operations later. And then you have a kind of information bottleneck. So the size of the image here is much smaller than the size of the image there. And then you can go up, you can make concatenations, you can make additions. So this is what we refer to when we say neural architecture, or the network architecture. So it happens that very often, for instance, it has been proved for instance, to recognize, to do face recognition, that you have an image as the input, and that all these input values from the image, they are fed into the first layer of the neural network, then second layer, third layer, and so on. And it has been shown that the first layer, once they learn to recognize faces, what the first layers, what they learn to recognize are these kind of patterns. So they are kind of edges, and then these edges are combined into higher level features. So these edges are combined into an eye, into a nose, into a mouth, and then these neurons respond to mouths, eyes, noses, and these are even further combined into more high-level hierarchy objects. And at some point, when you recognize your friend, one neuron is spiking very quickly, because you have seen the face of your friend, but it started in the low-level layers with just edge recognitions. And it has been shown that this happens in the computer, but it also happens in our brains. So our modular our brain modules that are related to visual information, they also behave in this way. Actually, the first layers, they also have this kind of inhibition behavior. So when one neuron activates, the nearby neurons are inhibited, and this is just a physiological representation of these edges. So there is here I'm showing a brief history of artificial intelligence and deep learning. So here you see the big names in the history. So these first models of the neurons, they started in 1940s, and they were just for mimicking the behavior of a neuron, and then the back propagation, and that was a first golden age around the 60s. But then they found this XOR problem, that is with the first neural networks that they had just one layer, they couldn't represent this function, that is a relatively easy function. And then we discovered back propagation, the names associated to this. So with the backpropagation, we could construct more complex neurons, and then convolutional neural networks came in at the end of the 1990s, and then there was again a big change with AlexNet. That was a very, very complex, very deep. This was the one that was making the deep thing. And so deep, many layers, neural networks, and then transformers, generative adversarial networks, and all the generative networks, and so on. So here, if you want, in this link, you can find the history of these networks in much more detail. And here also, when I put the link in the slides, it has two aims. One is to acknowledge where the image or the idea is coming from, and also for you to expand your knowledge. So you can go to that link, and normally it is very well explained. And making this review of the history of deep learning. So deep learning can be considered a subset of neural networks. So it is neural networks in which you have many layers. That is the name deep. And then neural networks is a subfield of machine learning algorithms, where the goal of machine learning is to find ways to learn and make predictions based on data. So here the emphasis is on data, and then this is a subset of artificial intelligence. So artificial intelligence is any technique that tries to mimic the human behavior. Now the most successful successful techniques are these deep learning, but they are not the only ones. Depending on what is the problem, very simple models can behave pretty well. So with this, we finish this very short session.